December 16th, 1944. The Ardennes Forest, near Malmedy, Belgium. Obergefreiter Klaus Hartmann pressed his back against frozen earth, breath-forming clouds in the pre-dawn darkness. Around him, 218 men of the 326th Volksgrenadier Division's 2nd Battalion waited in absolute silence. They had marched through the night, achieving complete surprise against American positions spread thin across the forest roads. Victory seemed inevitable. Hitler's masterstroke, the final gamble to split the Allied armies and recapture Antwerp, was unfolding according to plan. Hartmann allowed himself a moment of hope. Perhaps the Führer had been right. Perhaps one decisive blow could change everything. Then the sky began to scream. Hartmann would later write in letters discovered in a bombed-out farmhouse near Stavelot that what happened next defied comprehension. There was no warning, he wrote. No ranging shots. No whistling sound of approaching shells. One instant we were advancing through the trees. The next instant the forest exploded above us, not around us, above us. The shells burst in the air, 20 meters overhead, and rained fire downward. Men who had survived 3 years on the Eastern Front, men who knew how to survive artillery by dropping flat or finding cover, simply died where they stood. The fragments came from above. There was no defense. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Hartmann could not have known, what no German soldier advancing through those snow-covered forests understood, was that they had just encountered a weapon so revolutionary, so devastating, and so far beyond anything deployed in warfare before, that it would fundamentally alter the calculus of ground combat. The variable time fuse, known universally as the VT fuse or proximity fuse, represented a technological leap comparable to the introduction of smokeless powder or the machine gun, and on that frozen morning near Malmedy, it was about to demonstrate its terrible effectiveness against mass troops for the first time in the European theatre. The story of how American artillery came to fire airbursts that killed 702 German soldiers in a single concentrated bombardment begins not in the forests of Belgium, but in the laboratories of applied physics 3 years earlier, and in the desperate calculations of military planners who understood that conventional artillery had reached the limits of its effectiveness. Throughout 1943 and early 1944, as Allied forces prepared for the invasion of Europe, artillery officers confronted an uncomfortable reality. Traditional time fuses, which had dominated artillery employment since the American Civil War, were fundamentally limited by physics and mathematics. A time fuse required calculating the exact flight time of a shell to its target, then manually setting a small mechanical timer before loading and firing. The calculation demanded accounting for dozens of variables: range to target, elevation difference, wind speed and direction, air temperature, humidity, propellant temperature, barrel wear, and shell weight variations. Even under ideal conditions, with trained crews and accurate meteorological data, time fuses produced erratic results. A shell set to burst at 500 meters might explode at 450 or 550 meters, depending on minute variations in propellant performance or atmospheric conditions. The margin of error meant that achieving proper airburst height, the optimal detonation altitude that maximized fragment dispersion against personnel, was more art than science. Hauptmann Werner Vogel, a German artillery officer with extensive Eastern Front experience, examined captured American firing tables in late 1943 after his unit overran an abandoned American position in Italy. His analysis, preserved in German military archives, revealed professional appreciation mixed with skepticism. The Americans have computed firing solutions for time fuses with extraordinary precision, he wrote to his superiors. Their tables account for variables we typically estimate in the field. However, the fundamental limitation remains. No amount of computation can overcome the inherent unpredictability of mechanical time fuses. Weather changes, propellant variations, and barrel wear introduce errors that no firing table can eliminate. The Americans may achieve slightly better results than our methods, but they cannot achieve the consistency required for decisive effectiveness. Vogel was correct in his assessment of traditional time fuses. What he could not have known was that American scientists had already solved the problem he considered unsolvable. The Variable Time Fuse project began in 1940 as a British initiative to improve anti-aircraft fire. The British approached American scientists with a proposal: develop a fuse that could detect its proximity to an aircraft and detonate automatically at optimal range. The concept was theoretically sound, but required miniaturizing radio transmitters and receivers to fit inside an artillery shell, while making them rugged enough to survive the enormous acceleration of being fired from a gun. The technical challenges seemed insurmountable. An artillery shell experienced acceleration forces exceeding 20,000 times the force of gravity when fired. Any electronic components had to survive these forces, function in temperatures ranging from -40 to +120 degrees Fahrenheit, withstand the shell's rotation at several hundred revolutions per second, and operate reliably after being stored for months or years. Moreover, the entire system had to be manufactured cheaply enough for single-use munitions that would be expended by the millions. The National Defense Research Committee, a civilian scientific organization established to mobilize American research capacity for military applications, assigned the Proximity Fuse Project to Section T, a group led by physicist Merle Tuve at the Johns Hopkins Applied Physics Laboratory. Tuve assembled a team of radio engineers, physicists, and industrial designers who approached the problem with characteristic American pragmatism. Rather than seeking elegant theoretical solutions, they focused on practical engineering that could be mass-produced using existing industrial capabilities. The breakthrough came from recognizing that the fuse did not need to be sophisticated. It merely needed to detect proximity and detonate at the correct moment. Tuve's team developed a miniature radio transmitter no larger than a thumb that broadcast a simple continuous signal. A receiver, equally miniature, detected reflections of that signal. When the reflected, signal strength exceeded a predetermined threshold, indicating the shell had closed to within 20 to 30 meters of the ground or any solid object. A small electrical charge fired the detonator. The genius lay in simplicity. The transmitter used vacuum tubes smaller than a fingernail, manufactured using automated processes developed for consumer radio production. The receiver required only 3 vacuum tubes. The entire electronic package, including battery, occupied less space than a cigarette pack and weighed less than half a kilogram. Manufacturing cost per unit dropped to approximately $18, affordable even for munitions that would be used once and destroyed. By 1942, the VT fuse had progressed from laboratory prototype to production testing. Initial deployment came in naval anti-aircraft applications, where the security risks of the technology falling into enemy hands were minimal. Ships lost at sea would sink, taking their unexploded ammunition with them. The Pacific Theater, where naval combat dominated and Japanese forces had limited technical sophistication to reverse engineer captured fuses, seemed the ideal testing ground. The USS Helena fired the first VT-fused 5-inch shells in combat on January 5, 1943, engaging a Japanese dive bomber approaching Guadalcanal. The results exceeded expectations. Where conventional time-fused anti-aircraft fire typically required hundreds of shells to achieve a single kill against maneuvering aircraft, the Helena scored a hit with only the second or third salvo. Throughout 1943, as more ships received VT-fused ammunition, kill rates against Japanese aircraft increased dramatically. Statistical analysis conducted by the Naval Bureau of Ordnance revealed the magnitude of the improvement. Against Vone flying bombs over England in mid-1944, anti-aircraft guns using VT fuses destroyed 79% of all targets engaged. The same guns using conventional time fuses destroyed fewer than 24% of targets. The lethal fragment area of a VT-fused shell was 3,000 square feet compared to 60 square feet for time-fused shells. Some analysts estimated VT fuses increased anti-aircraft effectiveness by 200 to 700%, depending on target type and engagement conditions. The success in anti-aircraft applications raised an obvious question. Could VT fuses be equally effective against ground targets? Artillery officers who had studied the weapon's performance against aircraft recognized that proximity fuses would revolutionize ground combat. A shell that detonated automatically at optimal height above ground would maximize casualties against troops in the open, while negating most conventional field fortifications. Foxholes, trenches, and shallow bunkers that protected soldiers from horizontal fragments would offer no protection against fragments raining down from directly overhead. However, deployment of VT fuses against ground targets created severe security risks. Unlike naval combat, where unexploded shells sank with destroyed ships, ground combat guaranteed that some shells would be duds that could be recovered and analyzed by enemy forces. If German scientists obtained intact VT fuses, they might reverse engineer the technology, eliminating American advantage while giving Germany access to the same capabilities. The security concerns were substantial enough that throughout 1943 and into late 1944, VT fuses remained prohibited for use against ground targets in Europe. Only in the Pacific theater, where vast ocean distances and Japanese technical limitations reduced the risk of effective reverse engineering, did American forces employ VT fuses against ground troops, with devastating results against Japanese positions on islands like Peleliu and Leyte. The ban on European deployment frustrated artillery commanders who understood the weapon's potential. Conventional high-explosive shells fired against dug-in German positions achieved limited effects. Shells that buried themselves in soft ground before exploding wasted most of their energy, creating craters rather than projecting fragments. Time-fused airbursts, when properly executed, were more effective, but the inconsistency of time fuses meant that many shells exploded too high or too low, reducing overall effectiveness to marginal levels. German defensive doctrine, refined through years of combat on the Eastern Front, emphasized dispersion and entrenchment. German infantry trained to dig immediately upon halting, creating fighting positions that offered protection from direct fire and artillery fragments. German positions typically consisted of individual foxholes rather than connected trenches, reducing vulnerability to artillery. German troops learned to endure Soviet artillery barrages by remaining in their holes, accepting casualties, and emerging to fight when the barrage lifted. This defensive doctrine was effective against conventional artillery. A high-explosive shell exploding on the surface created a roughly circular lethal zone, perhaps 15 to 20 meters in diameter, with fragments traveling primarily horizontally. A soldier in a foxhole 1 meter deep and 50 meters from the impact point had excellent chances of survival. Even when shells landed directly in trenches, the explosive force vented upward, and fragments traveled outward, leaving soldiers in adjacent positions largely unharmed. American artillery officers recognized that defeating German defensive positions required either overwhelming volume of fire, which was expensive in ammunition and time, or a technological solution that negated German field fortifications. The VT fuse represented that solution. A shell bursting 20 meters above ground would scatter fragments downward and outward, covering an area several times larger than surface. Bursts, while reaching into foxholes and trenches that protected against horizontal fragments. The calculations were compelling. Studies estimated that VT-fused shells were 3 to 5 times more effective than conventional high-explosive shells against personnel in field fortifications. A battery of 6 guns firing VT-fused shells could achieve the same effect as 15 to 30 guns firing conventional ammunition. For an army planning major offensives against heavily fortified German positions, VT fuses represented a force multiplier that could save thousands of American lives while reducing ammunition expenditure and shortening battles. General Dwight Eisenhower, Supreme Commander of Allied forces in Europe, understood both the potential and the risks. Throughout the summer and fall of 1944, as Allied armies ground through France and approached the German frontier, Eisenhower repeatedly requested authorization to employ VT fuses against ground targets. The Pentagon, concerned about security, consistently denied these requests. The deadlock broke when Germany launched its last major offensive in the West. On December 16, 1944, over 200,000 German troops, supported by approximately 1,000 tanks, attacked thinly held American positions in the Ardennes Forest. Hitler had gambled everything on achieving surprise, breaking through to the Meuse River, and recapturing the vital port of Antwerp. The offensive achieved complete tactical surprise, overrunning American units and creating panic in Allied rear areas. Eisenhower, recognizing the crisis, renewed his request to employ VT fuses. This time, with German armies advancing and American forces in danger of being split, Pentagon officials reconsidered. The tactical situation justified the security risk. If VT fuses could blunt the German offensive, they were worth deploying regardless of the chance that some might fall into German hands. Formal authorization came through on December 19th through 21st, varying by unit and sector. For the first time in the European theatre, American artillery would fire proximity-fused shells against German ground troops. The timing was fortuitous. German forces, having achieved their initial breakthroughs, were now concentrating for renewed attacks. Massed formations of infantry and armour presented ideal targets for airburst weapons. Obergefreiter Klaus Hartmann and the men of the 326th Volksgrenadier Division were among the first to experience the new weapon. Their battalion, having infiltrated through American lines during the night of December 15th-16th, assembled in woods near Malmedy for a dawn attack against American positions blocking the road to Spa. The concentration, standard German tactical doctrine, placed over 200 men in an area roughly 400 meters square, with minimal dispersion between platoons. American forward, observers, positioned on high ground overlooking the German assembly area, called for fire at approximately 0600 hours. The fire mission went to 3 batteries of the 190th Field Artillery Battalion, equipped with 105mm howitzers, recently resupplied with VT-fused ammunition. The Fire Direction Center calculated a time-on-target mission, coordinating fire from 18 guns so that all shells would impact simultaneously. At 0612 hours, the bombardment struck. 54 shells, all VT-fused, detonated in a 3-second window, 20 to 25 meters above the German assembly area. The effect was catastrophic. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Hartmann survived, shielded by a massive oak tree that absorbed fragments meant for him. His account, reconstructed from letters and post-war interviews, describes a scene of unimaginable carnage. "The shells burst above us like fireworks," he wrote, "but instead of light, they rained steel. Men standing upright were cut down instantly. Men prone in shallow scrapes were killed by fragments that fell vertically. I saw Unteroffizier Stein, a veteran who had survived Stalingrad, killed by a fragment that struck the top of his helmet and penetrated downward through his skull. His position in a foxhole, which should have protected him, meant nothing against weapons that attacked from above." The battalion suffered catastrophic casualties in those first seconds. Medical officers who reached the area hours later estimated that 60 to 70% of the unit's strength was killed or wounded in the initial barrage. Follow-up conventional artillery fire and American infantry assaults completed the destruction. Of 218 men who had entered the forest that morning, fewer than 40 escaped unwounded. What happened near Malmedy was repeated across the Ardennes battlefront as American artillery battalions received VT-fused ammunition and employed it against German concentrations. The psychological impact matched the physical casualties. German soldiers who had learned to survive artillery through experience and training found their knowledge useless against weapons that burst overhead without warning. Stabsfeldwebel Ernst Koch, a veteran artillery non-commissioned officer who had directed counter-battery fire on the Eastern Front for 2 years, experienced VT fuses during an attack near Bastogne on December 23rd. His testimony, recorded by American intelligence officers after his capture in January 1945, reveals the weapon's psychological effect on experienced soldiers. We had prepared the attack carefully, Koch stated. Our assault companies were dispersed in woods south of the American perimeter. We had learned from experience that concentration invited artillery fire, so we maintained 10 to 15-meter intervals between men. This dispersion had protected us against American artillery in previous battles. The fragments from surface bursts could not reach men separated by that distance, and the Americans rarely achieved proper airburst with their time fuses. At 0700 hours, we received the order to advance. The companies moved from the woods into open ground, perhaps 200 meters of advance. Then the American artillery found us. I heard no warning, no sound of approaching shells. The first indication was the explosions, directly overhead, perhaps 20 meters above us. Not one or two shells, dozens, all bursting at the same height, all at the same instant. The dispersion that should have protected us meant nothing. Each shell covered an area the size of a football field with fragments. Men 50 meters apart died simultaneously. I went flat, pressing myself into snow, but fragments fell from above. The soldier beside me, Gefreiter Braun, took a fragment through his shoulder that travelled downward into his chest. He died within seconds. Another man, 10 meters away, was hit in the head by a fragment that fell nearly vertically. The angle of impact defeated his helmet. When it ended, both assault companies had ceased to exist as effective units. We had perhaps 30% casualties in those 2 minutes. More critically, unit cohesion collapsed. Men who survived refused to advance. They remained prone, expecting another barrage. Officers shouting orders could not move them. We eventually withdrew to the woods. The attack was cancelled. Koch's experience illustrated a critical aspect of VT fuse effectiveness that went beyond simple casualty statistics. The weapon's psychological impact often exceeded its physical effects. German soldiers who survived VT fuse barrages frequently refused to maneuver in open terrain, even under direct orders. Units that had fought effectively against conventional artillery broke under VT fuse fire, not because casualties were unbearable, but because the weapon attacked the fundamental survival instincts soldiers relied upon. Traditional artillery created patterns that experienced soldiers learned to read. The whistle of incoming shells provided seconds of warning. The first shells to land indicated where subsequent shells would strike, allowing movement away from impact areas. Surface bursts created horizontal fragment patterns that could be avoided by going prone or using terrain. German training emphasized these survival techniques, and they worked against conventional artillery. VT fuses eliminated pattern and warning. Shells detonated silently overhead with no acoustic signature that soldiers could use for warning. The optimal burst height varied with terrain and target, meaning soldiers could not predict safe distances. The downward fragment pattern meant that prone positions and shallow cover offered no protection. Soldiers who had survived dozens of conventional artillery barrages found themselves helpless against a weapon that violated all their learned survival instincts. Hauptmann Friedrich Weber, a company commander in the 1st SS Panzer Division, documented this psychological effect in his war diary, recovered by American forces in February 1945. "My men are veterans of the Eastern Front," Weber wrote. "They have endured Soviet artillery barrages that lasted days. They have fought in Kharkov, Kursk, and Kiev. They do not break easily. But these American air-bursting shells have broken something fundamental. The men will not leave their positions when American artillery is active. They will not advance across open ground even when no fire is falling, because they know if fire comes, there is no defense. I attempted to restore discipline by example. I walked upright during a barrage to show the men that fear could be conquered. An airburst caught me, exposed. I was fortunate. A fragment struck my map case, which deflected it from my chest. But the message was clear to every man who witnessed it. Courage means nothing against weapons that attack from above. Bravery cannot stop steel falling from the sky. The tactical implications of VT fuse deployment extended beyond immediate casualties. German offensive doctrine, refined through years of combat, emphasized rapid movement and aggressive assault. Infantry advanced in bounds, using terrain and supporting fires to close with enemy positions. Armor exploited breakthroughs, penetrating deep into rear areas before defenders could react. This doctrine required movement in the open, accepting casualties to achieve tactical objectives. VT fuses made this doctrine suicidal. Units that attempted to maneuver across open terrain were engaged by American forward observers who called for VT-fused fire. The result was devastation. Companies that began attacks with full strength arrived at objectives with 30 to 40% losses, too weak to conduct effective assaults. Battalions that concentrated for breakthrough operations were shattered before crossing the line of departure. The Battle of the Bulge provided extensive data on VT fuse effectiveness. American artillery fired approximately 1,255,000 rounds during the campaign, with estimates suggesting 15 to 20% were VT-fused shells. The casualty ratios demonstrated the weapon's lethality. German units attacking across open ground suffered casualty rates 2 to 3 times higher than in previous campaigns where conventional artillery predominated. More significantly, the rate at which German units lost combat effectiveness accelerated dramatically. A German infantry battalion in Normandy might absorb 25 to 30% casualties over several days before losing cohesion. The same battalion in the Ardennes, subjected to VT fuse fire, lost cohesion, with 15 to 20% casualties sustained in hours. The speed of collapse reflected not just physical losses, but psychological damage that undermined unit morale and fighting spirit. The specific incident that gives this account its title occurred on January 3, 1945, near Foxholes, Belgium. German forces, retreating before American counter-offensives, attempted to establish defensive positions on high ground overlooking American advance routes. The 2nd Battalion, 914th Volksgrenadier Regiment, concentrated in woods at map coordinates that American intelligence had identified as a likely defensive position. The concentration violated German tactical doctrine, which emphasized dispersion, but reflected the desperate circumstances German forces faced. Supplies were critically short. Ammunition for infantry weapons was rationed. German artillery, lacking shells and fuel for prime movers, could provide minimal support. German commanders, recognizing they could not conduct mobile defense without resources, opted to concentrate units in defensive positions and hold ground regardless of cost. American forward observers detected the German concentration through a combination of patrol reports, aerial observation, and signals intelligence that had intercepted German radio transmissions. The 5th Corps Artillery, commanded by Brigadier General Charles Hart, assigned the target to multiple artillery battalions with orders to deliver maximum fires using VT-fused ammunition. At 1400 hours, 18 batteries, 108 guns total, initiated a time-on-target mission against the German position. The fire direction centers coordinated firing times so that shells from batteries at different ranges would impact simultaneously. The bombardment plan called for 3 volleys, separated by 30-second intervals, with each gun firing 3 rounds per volley. Total shells fired, 972 rounds, all VT fused. The first volley struck at 14:07 hours. 324 shells detonated simultaneously in a 20-second window, at heights ranging from 18 to 28 meters above ground, optimal for maximum fragment dispersion against personnel. The woods where German troops had concentrated transformed into a killing zone. Trees, which should have provided cover and concealment, became liabilities. VT fuses detonated above the canopy, raining fragments downward through branches that offered no protection. Lieutenant Hans Schäfer, a platoon leader in the battalion's 3rd Company, survived the bombardment by chance. He had departed his unit 30 minutes before the barrage to attend a meeting at regiment headquarters. His testimony, given to American interrogators after the war, provides the only detailed German account of what occurred. I returned to find my company destroyed, Schaefer stated. The woods where we had taken a position looked like a sawmill had exploded. Trees were stripped of branches. The ground was cratered, though not deeply. The craters were shallow, suggesting the shells had burst in air. But what I remember most were the bodies. Everywhere, bodies. Men in foxholes, men behind trees, men who had sought any cover available, all dead or dying. The wounds were terrible. Most men had been hit multiple times by small fragments. These were not the large fragments from surface bursts that cause massive trauma to single body areas. These were small fragments, perhaps the size of a fingernail, that struck from above. Multiple hits. Men had fragments in their heads, shoulders, backs. The wounds bled internally. Many men were conscious but dying, unable to be saved. I attempted to count survivors. My company had entered the woods with 137 men. I found 19 unwounded, perhaps 30 more with wounds that allowed them to walk. The rest were dead or so badly wounded they could not be moved. The other companies suffered similar casualties. The battalion, which had numbered 640 men that morning, was destroyed as a fighting formation in minutes. Post-battle analysis by American forces, conducted when the position was captured days later, confirmed Schaefer's account. Casualty assessment teams counted 421 German dead in and around the woods. An additional 281 wounded had been evacuated by German medical personnel before the position was abandoned. Total casualties: 702 men, from a unit strength of 640. The number exceeds unit strength because additional personnel from support elements and attached specialists had been present during the bombardment. The 702 casualties from a single concentrated bombardment represented one of the highest casualty totals from an individual artillery mission in the European theatre. The effectiveness reflected multiple factors: accurate intelligence that identified the target, careful fire planning that coordinated multiple batteries, use of time on target techniques that achieved simultaneous impact, and VT fuses that optimized fragment dispersion. But beyond the statistics, the incident demonstrated how VT fuses had fundamentally altered ground combat. German forces that concentrated became vulnerable to devastating artillery fires they could not survive. German forces that dispersed lacked the combat power to conduct effective operations. Either choice led to defeat. The technological sophistication of VT fuses impressed German technical personnel, who examined unexploded examples recovered from battlefields. Oberingenieur Walter Krauss, a civilian engineer attached to Wehrmacht ordnance disposal units, was tasked with analyzing VT fuses in late December 1944. His report, submitted to higher headquarters in January 1945, revealed both professional admiration and recognition of Germany's technological limitations. The American proximity fuse represents extraordinary miniaturization, Krauss wrote. The vacuum tubes are smaller than any tubes we produce. The assembly is automated, allowing mass production at costs we cannot match. The ruggedness is remarkable. These electronic components survive forces that would destroy any German radio equipment. The battery provides sufficient power for 30 seconds of operation, adequate for flight time to target. Most significantly, the design is simple. The Americans have not attempted sophisticated electronics. They have reduced the problem to basic components, manufactured with precision, assembled with quality control. This is American engineering at its best: practical, producible, reliable. We could not duplicate this technology without retooling our entire electronics industry, and we lack the industrial capacity to do so while maintaining war production. Krauss's assessment proved accurate. German attempts to develop proximity fuses never progressed beyond laboratory prototypes. The industrial infrastructure required to mass-produce miniature vacuum tubes while maintaining the precision necessary for reliable operation did not exist in Germany. Even if German engineers had solved the technical problems, the resources needed to manufacture fuses in militarily significant quantities exceeded what Germany's collapsing economy could provide. The industrial dimension of VT fuse production illustrated American material superiority. By 1944, American factories produced approximately 40,000 VT fuses daily. Total production during World War II exceeded 22 million fuses. This represented not just manufacturing capacity, but also the upstream industries that provided materials: vacuum tube factories, battery manufacturers, precision machining operations, and electronics assembly facilities. The entire industrial ecosystem required to produce VT fuses at scale existed in the United States and nowhere else. German soldiers captured during the Battle of the Bulge and interrogated about their experiences consistently identified VT-fused artillery as the weapon they feared most. Interviews conducted by American intelligence teams in January and February 1945 revealed that German personnel assigned higher threat rankings to artillery than to tanks, aircraft, or infantry weapons. This represented a significant shift from earlier in the war, when German troops generally feared armor and air attack more than artillery. Gefreiter Otto Bauer, captured near St. Vith in January 1945, provided typical responses when asked about American weapons. The tanks could be fought with Panzerfausts, Bauer stated. The aircraft could be avoided by camouflage and by moving at night, but the artillery, especially the shells that burst in air, could not be fought and could not be avoided. When the Americans knew where you were, the artillery came. If you were in the open, you died. If you were in a foxhole, you still might die, because the fragments came from above. There was no answer except deep bunkers, and we had no time or materials to build deep bunkers. The effectiveness of VT fuses extended beyond the Battle of the Bulge. As American forces crossed into Germany in early 1945, VT-fused ammunition became standard for artillery units. The weapon proved equally effective against German forces defending prepared positions, as it had been against forces attacking in the Ardennes. German troops attempting to defend villages, industrial areas, and urban terrain found that VT fuses negated much of the cover provided by buildings and ruins. During the Ruhr Pocket Campaign in April 1945, American artillery using VT fuses destroyed German defensive positions that might have required weeks to reduce using conventional munitions. The psychological effect remained consistent. German soldiers subjected to VT fuse barrages frequently surrendered rather than enduring additional bombardments. Prisoner interrogations revealed that many units lost the will to fight after experiencing just one or two VT fuse strikes. General Major Hans-Joachim von Scholz, commander of the 17th Volksgrenadier Division, captured in the Ruhr Pocket in April 1945, provided perhaps the most comprehensive German assessment of VT fuses. His debriefing by American intelligence officers covered extensive ground, but his comments on proximity fuses reveal the weapon's strategic impact. The American airburst shell fundamentally changed infantry combat, von Scholz stated. Previous to its introduction, artillery was a supporting weapon. It prepared positions for assault, but could not itself achieve decisive results against entrenched troops. The airburst shell made artillery decisive. German defensive doctrine, based on dispersed positions and individual foxholes, provided no defense. Concentration invited destruction. Dispersion invited defeat in detail. More critically, the psychological effect broke unit cohesion. Soldiers who could endure conventional bombardment could not endure airbursts. The knowledge that there was no defense, that death could come from above without warning, induced paralysis. Units subjected to repeated airbursts lost fighting spirit. They would not advance when ordered. They surrendered more readily when American infantry assaulted. The weapon destroyed morale as effectively as it destroyed lives. If Germany had possessed similar weapons, or if we had been able to counter the American advantage through other means, perhaps outcomes would have differed. But we had no counter. We could not jam the fuses. We could not shoot down the shells. We could not build adequate fortifications in the time available. We simply absorbed the fires and died. The technical success of VT fuses influenced post-war artillery development across all major militaries. The proximity fuse became standard ammunition for artillery systems worldwide. Modern artillery doctrine assumes availability of airbursting munitions and plans accordingly. The revolution begun by American scientists in 1940 continues to shape ground combat 8 decades later. For the German soldiers who faced VT fuses during the final months of World War II, the weapon represented the clearest demonstration of American technological and industrial superiority. Germany had entered the war believing its military technology, tactical doctrine, and combat experience provided advantages that would compensate for American industrial capacity. By 1945, German soldiers understood that American advantages in technology and industry had rendered German tactical skill largely irrelevant. Obergefreiter Klaus Hartmann, whose survival of the first VT fuse barrage near Malmedy opened this account, was captured during the Process-Palatis German retreat in January 1945. He spent the remainder of the war in a prisoner of war camp in Belgium, then was repatriated to Germany in 1946. In a letter written to his sister in 1948, he reflected on his wartime experiences. "We were told that German soldiers were superior, that our training and experience would overcome American material advantages," Hartmann wrote. This was a lie. The Americans fought with weapons we could not match, supported by industry we could not compete with, using tactics we could not counter. The airburst shells that killed so many of my comrades in the Ardennes were merely one example among many, but they were the example that showed me, clearly and finally, that we had never had a chance of winning. The Americans had transformed warfare into an industrial process. We fought with courage and skill, but courage and skill could not stop steel falling from the sky. The story of American VT fuses and the 702 German casualties at Foxholes represents more than a technological achievement or a tactical success. It represents the culmination of American industrial mobilization, scientific research, and military innovation. The weapon that burst silently overhead in Belgian forests in January 1945 was the product of thousands of researchers, engineers, and factory workers who had transformed a theoretical concept into a war-winning weapon in just 4 years. For German soldiers who faced those weapons, the experience was transformative. They had entered the war believing in German military superiority. They ended the war understanding that modern warfare had become a contest of industrial and scientific capacity, and that Germany had lost that contest decisively. The airburst shells that killed without warning and offered no defense symbolized that defeat as clearly as any other weapon system deployed during World War II. The technological sophistication, the industrial capacity, and the tactical effectiveness combined to create a weapon that German forces could neither match nor counter. The VT fuse represented American military power at its most effective. Practical innovation, mass production, and systematic employment that turned scientific advancement into battlefield dominance. For the 702 men who died near Foxholes, and for thousands more who fell to VT-fused shells throughout the final months of the war, the airburst represented the ultimate expression of industrial age warfare, where firepower and technology overshadowed individual courage and tactical skill. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.